It's not a force, gravity. Who defines gravity? It would appear simple to respond to this query, but is it? Is gravity merely a force, or is there more to it? Humans on Earth normally consider gravity to be a force between two or more masses when they speak of it. I don't know about you, but whenever I think of gravity, I always see myself walking on a scale. When we step on a scale, the reading on the scale corresponds to the gravitational attraction of the Earth on our mass. This is what lends you credibility. That's a significant number in my instance. So, does gravity only represent the pull of our planet and provide us with a numerical value? You'll learn that gravity is much more than just a force if you watch this video with me to learn more about it. So, certainly, we are aware that the feeling of weight is caused by the gravitational force. We also understand that if we were on the moon, this pull would be weaker and we would experience similar difficulties maneuvering as these Apollo 17 crew did. Therefore, gravity is dependent on an object's mass and is not the same everywhere in the cosmos. This is a good place to start. Then, as you are aware, gravity is said to be what keeps the planets in their orbits. The powerful gravitational field of the Zeus is affecting them. Our solar system is in balance thanks to gravity, at least based on what we can currently observe. What is known is that when there are more than two bodies present, gravity behaves erratically. In that scenario, orbits evolve chaotically over very long time frames. When that takes place, some planets may be ejected from the star system and end up wandering aimlessly in the dark. But there are other powerful sources of gravity than stars. Consider the gravitational attraction of a black hole as an illustration. As you can see, pushing and pulling are simple concepts for forces. Today, we understand that although gravity can be thought of as a force, it is merely one aspect of a much larger phenomenon. The general relativity theory, which Albert Einstein devised in the 20th century, perfectly describes everything. He was such a genius, Einstein. He had to make a great leap and use critical thinking to distance himself from the prevalent views of science that were prevalent in his era. In particular, the theory of general relativity would not exist without a significant break from the concept of gravity as a force. Sure, GR is a beautiful theory and it makes sense mathematically. However, when it initially came out, people had a lot of reservations about it. Because extraordinary claims require extraordinary evidence, as Carl Sagan famously put it. But they quickly came across this proof. Einstein's theory, in my opinion, is a really remarkable claim, but it has also been supported by extraordinary data over time. There are a number of amazing experiments, for instance, that support the curvature of space and time. This is one of the most significant outcomes of the entire theory and is anticipated by general relativity. It essentially serves as the key to open the gate to a new realm. When he observed that everything in a gravitational field falls at the same rate, Einstein began formulating his theory. If you drop a hammer and a feather from the moon, they will both strike the surface simultaneously if you are standing there. The equivalence principle states that anything, regardless of mass or physical characteristics, is equivalent. All objects fall in the same manner, independent of their mass, so that, in the absence of any outside reference, both a free-floating spectator far from gravitational sources and a free-falling observer within the gravitational field of a big body experience the same thing. For instance, astronauts on the space station appear to be weightless and floating. In actuality, the Earth's gravitational attraction on the space station is almost as strong as it is on the ground. The space station and everything inside of it are falling, which is the difference. Since the space station is in orbit, it is actually circling the Earth. One of the most crucial presumptions Einstein used to construct his theory is that floating and falling are equivalent. Einstein claimed that the force of gravity is not a force between masses. Gravity is a force, but it is much more than that because Newtonian physics is still relevant. In a broader sense, it is a result of the warping of space and time that occurs when mass is present. Keep it straightforward so we may use an example. A straight line will be traveled by an item if there is no external force acting upon it, according to elementary physics. Consider making a line on a piece of paper, for instance. The line will no longer seem straight if you then twist or bend the paper, even though your hand is still moving straight. Similar to how space and time are bent, an object's straight course is also altered. Think about that for a second. It's merely paradoxical, so if it sounds challenging to you, it probably is. This explains, among other things, why everything falls at the same speed. Unintentionally, gravity warps spacetime in a specific way, causing all objects' straight paths to be bent similarly close to the Earth. A feather and a hammer will both fall at once. Thank you, Einstein, for the simple answer. What sort of experiment could so demonstrate that gravity distorts spacetime? How can we be certain that this is the case? Einstein postulated that light bends as it approaches a mass. Additionally, because the path is curved, it diverges from a straight line, lengthening the crossing time. In general, following a curve from point A to point B will take longer than doing it in a straight path. This effect, known as Shapiro time delay, applies to light. Erwin Ira Shapiro, an American astrophysicist and Timken University professor at Harvard University, was born in New York City on October 10, 1929. He has been a Harvard professor since 1982. The deflection of light was, at least theoretically, a well-known phenomenon. The deflection of light was already anticipated by Newton's theory. The difference is that general relativity predicts a twofold increase in deflection. Now, it is frequently maintained that because light has no mass, its path should not be affected by a body's gravitational pull. This isn't exactly accurate because light includes energy, and according to Einstein, energy and mass can somehow be equated via the well-known calculation E equals mc squared. Arthur Eddington made the initial observation of the effect in 1919. But before I tell you the narrative, I want you to consider this. How would you put the theories about light deflection to the test? Which circumstances must you meet in order to notice it? Keep in mind that we require a radiation beam that is traveling in our direction and a mass that is warping space between us and the source of the light. I'll give you a moment to consider it. Why don't you subscribe and click the notification bell in the interim? What did you think of it, then? For instance, the trick is to see the starlight during a solar eclipse. Eddington carried out this action in 1919. He went to the island of Principe, which is off the coast of West Africa, to capture a total solar eclipse on camera. The same area of the sky has already been captured on camera by him. Eddington was able to demonstrate how the apparent position of stars changed while the sun was close by comparing the eclipse shots to earlier images of the same sky. What's more, the degree of deflection proved that Einstein's calculations were accurate and not Newton's. That was incredible. A stunning illustration of the general relativity theory. We now know that when a cluster, another galaxy, or possibly a clump of dark matter comes between us, the observers, and the light source, the light from distant quasars and galaxies is deflected. Gravitational lensing is a well-known phenomenon that has been used to gauge galaxy masses and even see the impacts of dark matter. As one might anticipate, the deflection of light causes it to move along a longer, somewhat curved route. This indicates that light from a planet on the other side of the solar system from Earth arrives at a slightly later than we would anticipate. Shapiro made the initial measurement of this temporal lag in the late 1960s. Radio transmissions from Earth were reflected off Venus to demonstrate this when the planets were practically on opposite sides of the Sun. The measured round-trip delay of the signals was roughly 200 microseconds, which was in line with general relativity's predictions. It is much more than just a force, as you can see. However, these are not all of gravity's impacts. Let me explain gravitational waves to you. We stated that stars essentially alter the environment they are in. Now, allow me to ask you, what transpires, in your opinion, surrounding a binary star? These are star systems with only two parts. Similar to how spinning your finger in water causes ripples on the surface, they both bend spacetime and cause ripples in it. In addition, as a result of energy loss, the two stars steadily spiral closer to one another. They essentially collide into one another before merging. Their orbital period shortens as they draw closer and closer, moving faster and faster. So they have to use energy to get close. But how do they expend their energy? This will occur as a result of the gravitational wave release, according to general relativity. And indeed, this is what researchers Hulse and Taylor discovered while observing a neutron star that was rotating quickly. These stars also happen to emit radio pulses that are directed toward us. The two astronomers discovered that this specific pulsar's rate would accelerate up somewhat and slow down slightly at a regular rate, despite the fact that pulsar pulse rates are generally extremely regular. They demonstrated that the pulsar's orbiting of a star was what caused this change. Over time, scientists found their pulsar's orbital period was gradually getting shorter as they continued to study it. Simply explained, they were seeing a behavior related to general relativity. According to Einstein's hypothesis, the pulsar was and still is expanding due to the emission of gravity waves. Isn't that amazing? However, this is not the end. In addition, gravity is the cause of many more events. For instance, there's what is referred to as frame dragging. The Earth bends spacetime by its mass and twists spacetime around it since it is revolving on its own spin axis. Frame dragging is the name given to this distortion of spacetime. Because we've witnessed it, we are aware of it. How? The frame dragging is caused by the fact that the Earth's axis of rotation changes in a very accurate way when a gyroscope is placed in orbit around the planet. The gyroscope's orientation shouldn't change if there isn't any frame dragging. If there is frame dragging, the gyroscope will precess and its orientation will gradually change as a result of the spiraling motion of space and time. Guess what, though? This experiment has already been conducted with a satellite called Gravity Probe B. The 2004 experiment employed 4 incredibly accurate gyroscopes to detect frame dragging, or how much a rotating object pulls space and time with it as it rotates, as well as the alleged warping of space and time around a gravitational entity. While in a polar orbit around the Earth, GPB pointed at a single star, IM Pegasi, and used this information to determine both effects with previously unheard of accuracy. Well done, NASA. Do you still believe that gravity is just a force, then? Here's where the video ends. Thank you for viewing. I trust you had fun with it. See you on the channel again soon.